Good afternoon. My name is Jill or Lizzie from Singapore American School. My project presents the design, prototyping, and preliminary sensor validation of a smart automatic buckle system for biomechanical safety in running. I chose this topic because I love running. I'm in the school track and field team, so running has always been a crucial part of my life. Science is also one of my favorite subjects to learn in school. I decided to combine two of my favorite things and turn it into a project. Running causes progressive loosening of shoe fastening systems, altering foot-shoe coupling and increasing injury risks. Existing solutions such as traditional lacing, BOA dials, and Nike HyperAdapt offer comfort, but none detect instability or lock autonomously in real time. So, I hypothesized that a sensor-based smart buckle can detect the loosening cues and trigger autonomous locking within 85 milliseconds across speeds of 5 to 15 kilometers per hour using IMU-based gait detection and strap tension monitoring. The module has four functional layers: sensing with an MPU 6050 IMU and piezoresistive force sensors, processing via an ATmega 328p microcontroller running a finite state machine classifier, actuation through a miniature solenoid, and user feedback via a multicolor LED. A lithium polymer battery with a boost converter powers the system. The prototype uses off-the-shelf components totaling approximately $95. The microcontroller, IMU, breadboard, LED, and lace straps have all been required. However, force sensors, solenoid, and power supply are still pending. Assembly proceeded in three steps: component procurement, microcontroller power verification, and integrated IMU data streaming over I2C. All three milestones are complete. Testing spans three phases: benchtop calibration, instrumented treadmill trials at four speeds and three inclines with 18 participants, and field testing on a track and a trail. Outcome variables include locking response time, false positive and negative rates, and subjective usability. Three conditions were tested: sensor at rest, slow lateral translation, and vertical translation. Each produced clearly discriminable 6-degree of freedom responses from the MPU 6050. For key findings, the angular velocity magnitude feature achieved a 118-fold separation ratio between rest and motion, with a gap of 11.3 degree per second. A proposed threshold of 10 degree per second is predicted to yield perfect sensitivity and specificity on the benchtop dataset. Lateral motion concentrated variance on y-axis acceleration and z-axis angular velocity, while vertical motion concentrated on x and y respectively. These orthogonal signatures enable simple FSM classification rules without machine learning. Angular velocity outperformed acceleration by a factor of 118 versus approximately 7. This confirms the FSM should weigh gyroscope data more heavily for early-stage loosening detections. Key limitations include benchtop-only validations, low sampling rate, and incomplete hardware integrations. Next steps are upgrading to 100 Hz locking, integrating the force sensor channel, and commencing treadmill pilot studies. This project demonstrates feasibility of real-time biomechanical safety in footwear, from sensor signal to solenoid response in under 100 milliseconds. The system defines a new category of closed-loop safety devices with applications beyond running. Thank you.